Hi, I'm Sean, and welcome to my second YouTube content. Today, I'm going to be reviewing an SSCI academic paper titled Identifying Supply Chain R&D Partners via Multilayer Institutional Cooperation Network and Tailored Link Prediction. Just so you know, I'm going to mainly focus on the methodology part of this paper, since my YouTube channel is essentially purposed for providing information and insights specifically for AI applications. And also, I want to give you guys a heads up on the fact that this paper review pretty much left out some micro details. I didn't want to make my paper review into a 1 hour boring and tedious YouTube video, so I abbreviated the paper in my own way without leaving any core concepts behind. So basically, my explanation may feel like it left out a lot of the details, but that's okay, since my main purpose is to give you guys the main ideas of certain academic papers in a relatively short running time. Okay, now, let's get started. So, competition within supply chains is constantly heating up, and technology keeps evolving at a rapid pace. Because of this, relying solely on in-house R&D has clear limitations. That is why it makes much more sense for companies to seek the right R&D partner, making this a crucial and strategic decision in their business operations. Now, when it comes to R&D collaboration within supply chains, it's not just about similar organizations working together. There's actually plenty of room for collaboration even between companies at different stages of the supply chain. For instance, two raw material producers can certainly form a partnership, but collaboration can also happen between raw material producer and a company that processes those materials, manufactures products, and brings them to the market. This distinction is what we call horizontal collaboration, where similar entities work together, and vertical collaboration, where companies at different supply chain stages collaborate. As this study further goes on, with the core concept of supply chain, the authors broadly divide and interpret the real-life supply chain into three layers. First, we have the upstream layer, which includes institutions that supply raw materials, components, and basic materials. Next is the midstream layer, where raw materials are processed and components are assembled. And finally, there's the downstream layer, where the final product is developed and brought to the market. So looking at previous studies, we can see that two main methodologies have been proposed for selecting R&D collaboration partners. The first approach is indicator-based, where various evaluation metrics and scores are used to assess potential partners. The second approach leverages graph-based techniques, which analyze relationships and connections between entities to identify the most suitable partners. However, both of these approaches come with their own limitations. As the indicator-based method faces challenges in the discovery process itself, so it can be difficult to identify the right evaluation metrics, and it often fails to capture the dynamic nature of collaboration networks. On the other hand, network-based analysis is highly dependent on data availability. Like most AI-driven architectures, if there isn't enough data, it is inevitable that the accuracy for prediction drops significantly. These days, graph-based analysis techniques are being applied to a wide range of real-life situations. Given this trend, the authors of this paper highlight a key limitation from a supply chain perspective. The main issue is that previous studies have failed to integrate both intralayer information, meaning within a single layer, and interlayer information, meaning across different layers within supply chain networks. This lack of integration not only leads to information loss, but also results in lower prediction accuracy. To address these limitations, the authors propose a multi-layer network graph analysis approach. For data collection, they use patent data, where nodes represent applicants, in this case, institutions. They also define two types of edges. One, intralinks, meaning within layer links, represent collaborative relationships. The weight of each edge is determined by the number of patents co-filed by a pair of the nodes. And two, interlinks, meaning between layer links, represent supply-demand relationships. These weights are assigned based on a combination of intralink similarity and interlayer correlation. According to the paper, many previous studies have applied graph-based network analysis as a way to effectively identify collaboration partnerships. However, most of these studies have focused on building single-layer networks, which comes with certain limitations. One major drawback is information loss, and another is reduced computational efficiency. Eventually, these factors limit the effectiveness of single-layer approaches in capturing complex collaboration dynamics. Some previous studies have also explored multi-layer networks, and their findings are quite interesting. Compared to single-layer networks, multi-layer approaches allow for a richer and more comprehensive representation of information, capturing the complexity of relationships more effectively. So when it comes to multi-layer network analysis, there are two main methodologies. The first approach is based on similarity, where various metrics have been developed to calculate similarity across different network layers. The second approach involves machine learning and deep learning models for link prediction, which help uncover complex patterns within multi-layer networks. Now, let's go over the overall methodology. The multi-layer R&D collaboration framework suggested in this paper consists of three key stages. Number one, building the multi-layer network. Number two, identifying the potential R&D partners. And number three, evaluating the identified partners. So these three steps form the foundation for a structured and effective partner selection process. First, phase one, building the multi-layer network. Phase one is proposed for constructing the multi-layer network using patent data. In this process, applicants, meaning institutions, are represented as nodes. Then collaboration relationships are extracted from co-filed patents. So the number of shared patents between two applicants is used as the edge weight to represent the strength of their collaboration. So here are some details of the multi-layer network constructed in phase one. As different node colors represent different supply chain stages, the red nodes indicate the upstream stage, while green nodes and blue nodes represent the midstream stage and downstream stage, respectively. The solid black lines, which are non-dotted, indicated co-occurrence patents, meaning two institutions have collaborated on a shared patent. And then all dotted lines are represented as potential future links, classified into three colors: brown, gray, and red. The brown dotted lines indicate horizontal collaboration relationships, while the gray dotted lines connect the same institution across different layers, showing that an entity operates in multiple supply chain stages. Last but not least, the red dotted lines represent potential links that include both horizontal and vertical collaboration aspects. Let's look at some examples of the brown and red dotted lines for better understanding. First, take a look at the brown dotted line in the G1 layer, aka upstream stage, where there is a potential collaboration between nodes A and C. This connection exists because both A and C are linked to node J, suggesting that A and C might collaborate in the future based on their shared relationship with node J. Now, for an example of red dotted line, nodes A and E are not directly linked in G1. However, there is an existing connection between the two of them in G2 layer, aka midstream. This suggests that A and E are already collaborating in G2, so that there is also a high probability that a link might form between them in G1 as well. Another case of a red dotted line involves nodes J and I. In this case, nodes J and I do not currently have a direct horizontal collaboration with one another. However, since A is connected to J in G1 and to I in G2, this creates a logical pathway where J and I could potentially establish a future collaboration. These dotted lines help predict potential R&D partnerships by considering both direct and indirect relationships across multiple supply chain layers. Next is phase 2, identifying potential R&D partners. In this phase, the process begins with time sequencing the data by ordering it in time and then splitting it into past and future datasets. As obvious as it can get, the past data is used as data to predict future links, and the actual future data is used for validating the results of such predicted future links. The authors of this paper also used AUC, also known as area under the curve, as their primary evaluation metric. And then, extensive parameter tuning was applied to optimize the final results of this paper. And one of the key aspects of this study is the calculation of intralayer similarity to improve link prediction. The target layer, represented as alpha, is the layer where link existence is being predicted. The auxiliary layer, represented as beta, is an adjacent layer that complements the target layer with additional link prediction information. So to calculate intralayer similarity, this study applies 6 widely used link prediction baselines as shown in table A1. Estimating the probability of a link forming between nodes I and J within the same layer. Now, let's move on to how interlayer similarity is calculated. The probability of interlayer similarity is determined as follows. If the adjacency matrix value in beta is 1, it indicates that nodes I and J are actually connected in layer beta. To calculate the final similarity score, the model multiplies the intralayer similarity probability of nodes I and J in beta, and the correlation between the layers alpha and beta. On the other hand, if the adjacency matrix of beta is 0, this means that nodes I and J are not actually connected in that layer. In this case, the calculation follows a slightly different approach. First, the intralayer similarity probability of nodes I and j in beta is subtracted from 1. Second, the result is then multiplied by 1 minus the interlayer correlation value. So by applying these two conditions, the model ultimately determines the probability of a link forming in the alpha layer, the target layer. Now, let's briefly go over the formula used for calculating interlayer correlation, also known as AASN in this paper. The correlation value S measures how strongly two nodes, in this case I and J, in the alpha layer are influenced by their connections in the beta layer. Ki and Kj represent the number of connections that nodes I and J have in alpha. On the other hand, K beta I and K beta J represent the number of connections for nodes I and J in beta. So basically, the formula is saying that if nodes I and J have a high number of connections in beta, they are more likely to form a link in alpha. Conversely, if I and J are not connected in beta at all, the probability of them forming an interlayer link in alpha becomes 0. Finally, let's take a look at how the final integrated link prediction formula works. In this formula, the intralayer probability and interlayer probability for nodes I and J are each multiplied by parameter theta. Then the result is combined with 1 minus theta to balance the contribution of both intralayer and interlayer probabilities. Then the two values are summed to produce the final link prediction score. By the way, FYI, the parameter theta is a manually set parameter introduced by the authors. It is a real number between 0 and 1, allowing for flexible weighting between intralayer and interlayer probabilities. In conclusion, by integrating both intralayer and interlayer link probabilities, the final integrated link prediction model achieves highly precise R&D partner identification. And then, in order to assess the effectiveness of the R&D partner identification model, the authors validated its predictive performance using AUC results. By analyzing such AUC scores, they were able to measure how accurately the model predicts potential R&D collaborations, ensuring its reliability in real-world applications. And so, to summarize the methodology, it is important to understand three main key concepts. The first concept is to understand the intralayer similarity and horizontal collaboration. So the model applies 6 link prediction baselines to calculate intralayer similarity and identify potential horizontal collaboration links in the target layer alpha. As shown in figure A, the top left figure, institution nodes A and B both collaborate with node C. Therefore, as depicted in figure B, the top right figure, A and B are likely to collaborate in the future due to their shared connection with C. Then it is important to know the interlayer similarity and vertical collaboration. This step focuses on calculating interlayer similarity, which helps identify potential vertical collaboration links between the target layer alpha and adjacent layers. For example, in figure C, the bottom left figure, institution nodes A and E have a potential future collaboration. This is due to the fact that A collaborates with C in the upstream layer, while E collaborates with C in the downstream layer, forming an indirect link between A and E. Last but not least, it is crucial to understand the final step of optimizing theta and the final integrated link prediction. So the model finds the optimal theta value, integrating both horizontal and vertical collaboration results into a unified calculation. As shown in figure D, the bottom right figure, this approach provides a framework for identifying both intralayer and interlayer potential R&D partners, suggesting a tailored link prediction method seen in the title of this paper. Now, let's move on to phase 3, which focuses on evaluating the identified R&D partners. While the link prediction model successfully identified potential partners, not all node pairs were deemed suitable for R&D collaboration. As addressing this problem, an additional evaluation process was conducted to refine the selection process and ensure that only the most relevant partners were considered. Ultimately, this step helps filter out less viable collaborations identified and enhances the overall quality of R&D partner recommendations. To assess the suitability of identified R&D partners, this study established 3 key evaluation criteria: technological capability, collaboration ability, and collaboration potential. Such criteria is assessed in an integrated manner, eventually evaluating the patent holdings of each company, or assessing the technological similarity between institutions to determine compatibility, or even considering various factors that indicate the likelihood of a successful partnership, or even using the degree centrality to give an overall sense of an institution's cooperation capability, and more. And next, I would like to introduce the case study that this paper had to offer. For the case study, the authors focused on underwater mobility technology, or should I say underwater vehicles, which includes examples like submarines and underwater drones. This certain technology domain was chosen because of the growing market demand and the increasing need for marine resource exploration and environmental monitoring, which is why the authors applied their multi-layer R&D cooperation framework to this case study in order to determine whether or not the framework is applicable in real life. Now, the authors built a 3-layer network using patents directly related to underwater vehicle technology. The patent data was collected from the Durant Innovation Index, covering periods from the years 1996 to 2023. Then they classified patents into upstream, midstream, and downstream layers using specifically designed search queries based on business scope and technology-related keywords. To evaluate their approach, the authors compared their proposed methodology with GOR, also known as Global Overlap Ratio, a traditional method for measuring interlayer similarity. GOR assumes that the influence from upstream to downstream is the same as the influence from downstream to upstream. However, supply chain relationships are typically asymmetric in real-life situations. For instance, while upstream institutions may focus on providing raw materials, downstream institutions may specialize in assembling and commercializing the final product. Since these roles are fundamentally different, their relationship is inherently asymmetric, making the traditional GOR assumption less applicable to real-world supply chain. Such assumptions are to be proved by the correlation analysis conducted by the authors using a heat map. As you can see in Figure 7, the correlation between upstream and midstream layers was higher than that between upstream and downstream layers, and the same pattern was observed in reverse. This suggests that adjacent layers in the supply chain exert a stronger influence on each other compared to the layers that are further apart. Since midstream entities are always directly connected to either upstream or downstream entities in a real-world supply chain, these heat map findings provide meaningful insights into the structure of supply chain relationships. And to further validate the comparing of GOR and this paper's tailored link prediction, the authors compared the AUC values between GOR and their proposed methodology. As shown in Table 3, in most cases, the AUC value for the proposed method outperformed that of GOR, demonstrating improved prediction accuracy. Although, in a few instances, GOR had some higher AUC values, of course. But despite this, the authors claim that the key takeaway is their proposed method successfully incorporates the asymmetric nature of real-world supply chains, of which GOR does not account for. Then, after gathering the optimal results, the authors ranked the identified R&D partner pairs and selected the top 10 institution node pairs for each layer. The ranking process was conducted using 4 different tools. Number 1, Topsys, a technique for selecting the ideal alternative based on Euclidean distance. Number 2, Entropy-weighted Topsys, an improved version of Topsys where weights are assigned using entropy. Number 3, PSO-optimized Topsys, a further refined method where particle swarm optimization, aka PSO, is used to optimize weight allocation in Topsys. And number 4, radar chart analysis, a multi-dimensional visualization tool used to compare and analyze each alternatives. For specifics, this radar chart visualizes the evaluation results where each axis represents a different assessment metric. In this case, as the larger the area is covered, the higher the overall recommendation score for that certain R&D partner. As the result for the upstream layer, the TOYT GENE node pair had the largest area in the upstream, indicating high potential for R&D collaboration. For your information, TOYT specializes in automobile manufacturing, and GENE has strengths in electrical engineering and material science. A qualitative assessment suggests that GENE can complement TOYT's technological capabilities, particularly in developing protective materials with high pressure resistance and corrosion resistance, and advancing key components such as sensors and motors. Ultimately, this analysis highlights TOYT and GENE as an ideal R&D partnership. Now, for the midstream and downstream layers, the CSHI and SHAN node pair had the largest area in both midstream and downstream layers, demonstrating the strongest collaboration potential. While CSHI specializes in shipbuilding and engineering, SHAN focuses on marine equipment and ROV, also known as remotely operated vehicle. Through another qualitative evaluation, the authors state that these two companies are highly relevant to each other in terms of technological competence. The authors particularly suggested a simulated assumption in terms of collaboration between these two institutions, For a simple example, it was shown that CSHI's power management system could be effectively integrated with SHAN's detection devices, leading to optimized performance. Now, before concluding, let's go over the discussions suggested in this study, specifically pointed out by the authors. There were two aspects in which the authors suggested as important limitations of this study. Number one was the severe dependence on patent data. As it may be obvious, this study relies solely on patent data as its primary data source. So the authors suggest that expanding the types of data can include additional information sources, which may provide richer insights and improve the robustness of the findings. Next was the lack of consideration for technological attributes. As the current approach in this paper does not explicitly incorporate technological properties, the authors say that in future research, they are willing to integrate both technology networks and institutional collaboration networks. That way, this study would allow for a more comprehensive investigation of knowledge diffusion in potential R&D partnerships. So that is it for today. If you have anything you want to say or any feedbacks you want to give, please leave a comment down below. And if you want to catch up with future content, feel free to press the like button and subscribe. Well, have a nice day. Bye.